Hello, and welcome to today's webcast. My name is Dennis Semeka, Associate Editor at Vision Systems Design. The speaker for today's webcast, Machine Vision for Warehouse Automation and Intralogistics, is Mario Bohnacker, Head of Solutions at MVTec Software. A few housekeeping items before we begin. If you have questions or issues during the webcast, please click in the Ask a Question area at the bottom of the console. We'll try to answer as many of your questions today as possible. If you experience audio issues during the webcast, please try refreshing the page. If this doesn't solve the problem, or if you have any other issues during the webcast, please click in the Ask a Question area of the console, tell us about the issue, and a member of the webcast support team will work with you to correct your issue. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage. The slides will also be available for download today. These can be accessed via the Event Resources tab under the Ask a Question area. Before we begin, I'd like to thank today's sponsor, MVTec. Now, it gives me great pleasure to introduce Mario Bohnacker.
Thank you, Dennis. Welcome, everybody, also from my side. My name is Mario Bohnacker, and I'm the head of the solutions team at MVTec. The solution team mainly takes care of customer-specific projects and training with our products. Today, I want to talk to you about machine vision in warehouse automation and intralogistics. We will explain how these industries can benefit from machine vision, show you what kind of applications can already be solved with machine vision and what kind of applications will profit of the fast development of machine vision technology in the future. The agenda for today will feature the following topics. At first, we will give a very brief introduction of Emitech and our software products. In the following, we will show what kind of tasks in intralogistics and warehouse automation can benefit from machine vision and which machine vision technologies are suitable here. Afterwards, we will have a look at the typical process chains related to intralogistics and warehouse automation and explain which of the previously mentioned machine vision technologies can help to tackle the challenges of each of these process steps. So let us start with a quick introduction of Emitech. Emitech is a leading international manufacturer of software for machine vision with its headquarters in Munich, Germany. Currently, approximately 160 employees are working on mainly two software products. One is Merlik. Merlik is a powerful all-in-one machine vision software product that enables you to quickly build complete machine vision solutions by drag and drop configuration. You do not need any programming skills. It includes a designer for user front ends, and its complete framework is expandable with HALCON. The other one, which I just mentioned, HALCON, is the comprehensive standard software library for machine vision with an integrated development environment called HDevelop that is used worldwide. It is optimized for the needs of OEMs and system integrators and allows engineers to set up and program their own solutions for specific machine vision tasks. Furthermore, Emitech develops customized solutions from consultancy, feasibility studies, and prototypes up to integrated products. These software solutions can be based either on standard PC or embedded hardware like, for example, ARM-based systems. Moreover, Emitech's team has an excellent background in processing images of different kinds, including 3D data, infrared images, hyperspectral images, and X-ray images. Emitech products are made in Germany, developed at our competence center in Munich. Our services and products are distributed worldwide via our extensive distributor network. In the US, the Emitech LLC works out of Quincy, Massachusetts to better attend the North American market. So wherever you are situated, our highly qualified distributors are located close to you. Enough information about Emitech so far. Now let's have a look at machine vision technologies warehouse automation and intralogistics can benefit from. We want to start with a simplified process chain in intralogistics and warehouse automation. This process chain visualizes the steps between the supplier and the customer. The first step is goods received. Products usually arrive in boxes on pallets and need to be prepared for storage. The second step, the preparation for storage. This step may include unboxing of the products, identification of the goods, a comparison of the content to the parts list, and possibly a quality control of the delivered items. After preparation, the goods will be stored. In this case, storage positions and status must be known, like, for example, where the specific goods need to be stored, is there enough storage space, and so on. Halfway through this process, the goods are stored and wait for orders to be retrieved. For retrieving the goods, either boxed or unboxed, they need to be somehow identified and located to be able to pick and collect everything as desired. In the commissioning step, the goods need to be boxed. Before the boxing, a final quality control of the product might be useful to make sure the product left the storage without any damage. And finally, the packed goods are palletized and made available for delivery. Before we dig deeper into this process step and explain how they can profit from machine vision in particular, let's check out what kind of machine vision technologies may generate added value at all. Therefore, we exemplarily visualize two tasks which are interesting and might appear in several of the previously mentioned process steps. The first one is item picking. In order to be able to pick any item, the item needs to be identified. Somehow it needs to be determined in which way the item can be handled. In particular, this, for example, means, does the item have a hard surface or maybe a soft texture? Is special care needed? When this kind of questions are answered, we finally need to determine the gripping points at the item to be able to pick these parts automatically. The second task mentioned here is item inspection and shape or volume detection. Here we also want to identify the item first. Based on the type of the item, a visual quality inspection can be performed. For example, we can inspect parts or boxes for transportation damages. Thinking about saving packaging material, you might want to determine the size and the volume of an object in order to determine the perfect packaging strategy. Exemplary for these two tasks, we will now explain different machine vision technologies which can be used to solve these tasks. So we start with the identification of items. As of today, the identification of items based on a barcode is very popular. There are several different types of barcodes available, and these barcodes can come in different sizes and shapes, and so far this is one of the easiest way to identify items and is already used quite a lot. By the way, all the code types mentioned here and in the following are codes which can be read using MVTec HALCON, and also all example images which you will see in this webinar can be found as a standard example in our software. Coming back to barcodes. One challenge in reading barcodes is that the codes due to transportation speed or size appear blurred or with quite small resolutions in the image. In some cases, even by eye, it's difficult to see where one bar starts and the other one ends. New machine vision algorithms are able to robustly detect and decode even such kind of barcodes, which you can see on this slide. Another challenge, of course, are defect codes. During transportation, the labels might get damaged, or due to packaging, the code might be behind plastic foil or similar. It is possible to even decode barcodes with defects that lead to incomplete scan line. This is done by merging the scan lines if no valid scan line can be found. And as you can see in these examples, even strongly damaged, overpainted or covered barcodes can be read very robust and accurate. Most commonly, barcodes are printed in rectangular shape. But in some cases, the material or the shape of the items doesn't only allow a coding in alternative shapes. In this example, the barcode is printed circular, what is not a difficulty at all for reading this barcode. Another possibility to identify items is to use data codes. So what is the difference between barcodes and data codes? In machine vision, we differentiate between these two codes because of the dimensions in which the information is stored. In barcodes, the information is only stored in one horizontal dimension, and in data codes, the information is stored in 2 dimensions. So the main advantage of data codes is that more information can be coded in less space. There's a quite high number of different code types available, which is steadily increasing due to the fact that industry wants to add more and more information into such kind of codes. The challenges faced reading data codes are basically the same like when reading barcodes. Codes might be damaged, they might be disturbed, or the usually necessary quiet zone around the data code, which visually clearly separates the code from the background, is disturbed or non-existing. For example, you can see the image on the upper left for an example of a code without quiet zone. Most recent machine vision algorithms tackle these challenges, leading to a robust and fast decoding of the information. Besides data code and barcodes, some items may be equipped with any kind of label presenting any kind of text or characters. In such cases, optical character recognition, short OCR, might be an option to identify items based on text. These texts can come in different fonts, sizes, or even printing styles like, for example, dot print. An example for dot print code can be seen and the image on the lower middle and lower right. So far, we were talking about any kind of codes or label which can be used to identify the item. But how great would it be to identify any item in case there are no codes or labels available? For example, the items are too small to print labels on, like you can see the small screws in the image on the upper left, or the shape of the items vary too much, especially when it's necessary to identify natural products like fruits, for example. Nowadays, there is a solution for this kind of problem. The solution for this kind of problem is called deep learning. Deep learning allows you to classify and detect different items inside an image. So, in machine vision, there were already powerful classification algorithms available before deep learning. So several questions arise. What makes deep learning so powerful? Why can deep learning help here now? Or what is so different using deep learning in machine vision compared to existing classification algorithms? Let me explain why so far classification of items without codes or labels was so difficult and cumbersome. For this, we visualize the typical process steps of traditional machine vision classification. A little simplified, coming from input images to the classification results consists of 2 steps. The first one is we extract features like shape, texture, and intensity from the image, which means a software engineer needed to program an item-specific algorithm to extract information like size, shape, or texture. In the second step, we use these features as input for the classifier. The biggest effort in a classification application is this extraction of these features. And to be more precise, actually it's the selection of the right features which are significant to distinguish between different items. For a low number of parts, which in best case look totally different, this might be a manageable effort, but thinking of thousands of items which might be stored in a warehouse, this is a way too huge effort. So what is different using deep learning? The big difference with deep learning, not only the classification is trained, but also the features are learned automatically. Actually, all steps are learned. So there's no need to handcraft any features because deep learning automatically learns and extracts these features. Imagine these features as useful patterns that help machine learning models to differentiate between classes. For example, to decide if the given image shows a cat or a dog, easily spoken. Extracting such useful patterns is essential to achieve good prediction results. The basic principle of deep learning consists of two major steps. The first one is training. To train a deep learning network, we need labeled data. Depending on the deep learning technology you want to use, the kind of labeling differs, and more information on these different deep learning technologies will be provided a few slides later. These images and the corresponding labels go into the training, and the system learns the features which allow the classifier to distinguish between these classes. This is an iterative process in which the network optimizes its internal parameters and weights until wrong classification is optimized to a minimum. So instead of programming the feature extraction for each item type, we just need to provide images of each of the items to distinguish to the deep learning training. In usual machine vision applications, this is done as an offline step. And once the system has been trained, we input new images to the system which the system has never seen before. In typical machine vision applications, this actually is the production or online phase. The deep learning network, which here is visualized as the brain, calculates the learned features, applies the classification, and finally outputs the class, for example, a type of defect or the class of an item. In HALCON, so far there are three different kinds of deep learning technologies available. The first one is called classification. Classification classifies the complete image. This means only one object is allowed to be inside the image. A typical application for classification is a OK, not OK decision, as it's shown here for bottle mouth inspection, or the classification of, for example, natural products, in this case, fruits. Deep learning object detection is a technology to detect objects inside an image. In this case, multiple objects can be represented in one image, and as a result, the algorithm will return bounding boxes of the detected objects. A typical example for object detection, as you can see here, is detection and identification of overlapping objects, like, for example, in this image, the apple on top of the chocolate cereal package or the can on top of the noodle package, which can be detected even if they are placed on top on each other and overlapping. The third technology is called deep learning segmentation. Deep learning semantic segmentation can be used to segment objects inside an image pixel precise. As a result, the algorithm will return a class ID for each pixel inside the image. And using these technologies, the exact shape of any object can be segmented. So the semantic segmentation can, for example, be used to locate defects and determine the exact size and shape. Besides the examples already shown, further typical applications for deep learning are the detection of object instances in an image with orientation, which you can see here on the left, and counting and grasping of instances, which is shown an example on the right. Especially for counting, deep learning object detection is perfectly suitable. Its ability to detect even overlapping items allows a very robust counting and classification of the objects. Further examples for semantic segmentation can be seen here. On the left, you see how deep learning detects the exact size of arbitrary shaped objects, like in this case, vegetables. And on the right, you can see a defect detection on pills. Of course, such kind of defect or damage inspection could also be applied on boxes, for example. Coming back to the task overview, we just learned that deep learning can help to identify any items. As you have seen in some of the slides, deep learning is also suitable for quality control, for example, to detect defects. This opens up for new possibilities in inspecting the quality of items. By identifying the item, deep learning enables to determine an optimized handling strategy for goods or items. For example, by deep learning, you might classify if the item has a hard surface for a common gripper, or maybe a soft surface which need to be grasped by a vacuum gripper, for example. Okay, so far we talked about the first steps like identifying the item. In item picking, the next step would be to determine grouping points, or in the item inspection, you might want to determine the size and the volume of the item. Let's have a look which machine vision technologies can be used to tackle this kind of tasks. The first technology we call 3D shape-based matching. This technology allows to locate 3D parts in a 2D image. Here you can see some example images in which the 3D position and orientation is detected and could be used to guide a robot to grip the part. As you can see, the parts can also be partially occluded and must not be separated at all. So how does this technology work? Based on previously known information, for example, a 3D CAD model, it is possible to detect the 3D position and orientation of a part in the 2D image. Using the CAD model, a 3D shape model is generated. And this model consists of several 2D views of the objects from different perspectives. Finally, the algorithm tries to locate the best matching perspective inside a 2D image based on the contrast of the contours. Another technology is surface-based matching. As the name already indicates, this technology matches known surfaces into a point cloud. In difference to 3D shape-based matching, for which only 2D images are needed, 3D point cloud data is needed for surface-based matching. It is possible that scene and object data come from a variety of different sources, such as stereo sensors, time-of-flight sensors, sheet-of-light sensors, multi-view stereo sensors, or the CAD model from a 3D file. To train these algorithms, there are two possible ways. The first one is that the model is simply trained from a CAD file, and the second one is that the model is trained from a reference image, for example, from a 3D sensor, where a reference part is reconstructed once. HALCON supports the formats DXF, PLY, OFF to read CAD data from external programs. Even though surface-based matching works reliably and robustly for objects with a distinctive 3D geometry, it might produce mismatches for objects such as boxes, which have larger planar sides. For example, the object might be found in the background plane or slightly rotated. In this example, you can see that only using 3D point cloud information, the box might lead to an error in some case. So here you see in red the upper right box. It is not matched completely correctly. You can easily see that it's slightly shifted. Especially in this kind of cases, if you want to find boxes, it is recommended to combine the information of 3D point cloud with 2D image information. As you can see, the scene is acquired by a 3D sensor and additional 2D camera. But note, many of the sensors, such as stereo systems or time-of-flight sensors, already produce an intensity image at no additional costs. So using this 2D image and the edge-supported surface-based matching allows to refine the scene with this additional information. So the surface model is aligned such that it matches both the 3D data and the edges in the intensity image. So adding the 2D image information for edge extraction allows the algorithm to correctly identify the box position. So always keep in mind, if possible, try to combine all available information to get the most robust solution for your task. Besides the grouping position of an item or good, you might also be interested in the size or the volume of the items. 3D point cloud analysis allows you to determine the exact volume of arbitrary shaped items. Other possibilities are to estimate the bounding boxes of the items to roughly measure its extents. This information can, for example, be used to calculate packing positions. To use this information, to most efficiently generate or use the packaging space which is available, or to estimate the weights of items. Talking about 3D point clouds, one question, of course, is how to acquire these point clouds. There are several systems for point cloud acquisition. We'd like to mention two of them at this point. The first one, which you can see on the left, is a sheet of light system. In sheet of light systems, an object moves below a laser line, and this laser line is captured by a camera, and by the deviation of the line, the system is able to generate a 3D point cloud of the part. Especially for moving scenarios, like for example products moving on conveyor belts, this technology is highly suitable. The other one is stereo vision. Using stereo vision, 2D images of at least two cameras looking at the same objects are acquired at the same time. Based on the information of these images, a 3D point cloud can be calculated. The images shown here visualize the principal structure of such setups. For industrial use, there are ready-to-use 3D sensors and cameras on the market. The processing speed and accuracy of this kind of sensors increased a lot in recent years and will be rapidly enhanced in the future. Coming back to the task overview, we now learned how 3D technologies can be used to grip items and guide robot systems. We also learned that these technologies can be used to measure dimensions and volumes of items, for example, determine the most efficient way for packaging. So far, we learned that specific tasks can benefit from deep learning and 3D technologies. Deep learning is a quite new technology, but 3D machine vision is available since several years. So why does this technology get more and more interesting now and in the future? The answer to this can be found in the hardware development. If you look at the computing power, especially of embedded devices, you can see that in the last 5 years there was a big boost due to the smartphone industry. Due to this, the embedded devices nowadays have enough computing power available to run machine vision algorithms. And due to the advantages of embedded devices, they can be used in applications in which other hardware, like for example an industrial PC, was too expensive or too big. This development of computational power over the last years allows to use this kind of devices even for 3D machine vision algorithms. Previously, the computing power of such devices simply were not high enough to do 3D machine vision in an acceptable time. As the future developments will increase the computational power of such devices, they will get more and more industries for industry like yours. Besides that, embedded devices also have further advantages to common industrial PCs. Just to mention the compactness. Embedded devices usually have a very small number of pieces, so they are easily to build in, to remove, or to change. They are quite cost efficient because they are reduced to the essential and they have no annoying peripheries. Basically, they are power and communication, and that's it. And another advantage is they don't have any moving parts, like for example hard disks or fans or else, so there's a small default risks. And another advantages are, of course, low power consumptions and the remote possibilities of such devices. And coming back to deep learning, even for the use of deep learning, embedded devices are already usable. Whereas the training of a deep learning classifier in HALCON requires a graphical processing unit, the interference can also be executed just on a CPU. And this includes ARM-based CPUs. This means even deep learning tasks can nowadays be done on such embedded devices. Good. At this point, let's go back to the common process chain in intralogistics and warehouse automation. So far, we learned what kind of machine vision technologies can help in intralogistics and warehouse automation. Now, let us have a closer look at each of the process steps and see how in particular these process steps can benefit from machine vision. First process step was the goods receipt. The first step, goods most commonly are delivered on pallets, as you can see in this sketch here. So the first task is to depalletize the goods onto, for example, a conveyor system. Using mentioned 3D technologies, the position of the single palletized boxes can be detected and the robot can be guided to pick the single items and place them on a conveyor system. Here on this slide, you can see a few images as an example how this application could look like. And as mentioned, surface-based matching could be used in this case to detect the position. For easily shaped objects, even a primitive fitting, like for example fitting a cylinder, will also be a suitable approach. Another process during goods received is to read and decode bar and data codes. With common 2D camera systems or ready-to-use 2D smart cameras, this task can be solved very easily. Just to recap, these codes can be disturbed or damaged in a lot of different ways. And the same goes for the data codes, like for example the one at the lower right. Here the label is damaged and even a part of the code is missing. Still the code can be decoded, or the one in the lower middle where a punch hole cut off parts of the code, but still code is able to be read. During preparation for storage, there is the possibility for incoming good inspection. Either to inspect if the goods quality is as desired or to do a completeness check which compares the delivered items with the delivery list. In the shown scenario, a 2D camera takes an image of the open box and using identification algorithms, the content of the box is detected. In this case, the identification either can be done by reading the mentioned codes, but can also be done with deep learning for objects without labels. Especially the previously mentioned deep learning object detection can be applied here, as it is able to identify even overlapping objects. The ability to identify even the overlapped objects can be seen here in the image in the lower center. Here, several coffee bags are placed very close to each other, like they would be placed in a box, and the algorithm is able to detect each of the bags as a separate instance. And the same goes for the image in the lower right, where a completeness check of a bag of pills is performed to verify that each pill type is represented once. Due to the movement of the pills inside the bags, they can even touch or overlap quite a lot. In the next process step, the storage step, one task you need to solve is to identify shelf slots which are available, or you want to know which shelf slot has the most efficient dimensions to store the item or the box. In this case, you can use deep learning to check if shelf positions are empty or already occupied, and additional information of the positions like the dimension can easily be determined with standard machine vision algorithms. As an example, you may have such kind of storage shelf and you want to know which position area are available and which are occupied. So the final result of such an algorithm could look like this. Here the green areas visualize the free storage slots. Actually, there's one real-world application in which deep learning was used to solve this kind of problem. In this application, a mobile robot was equipped with a camera and taking images as passing by the shelf. And the original solution for this task was to use multiple 3D sensors to scan the content of the shelf. Therefore, the hardware setup was quite expensive. Using deep learning, it was possible to use only one 2D image. So there was quite a big cost reduction due to cheaper hardware. And besides that, besides saving the money by cheaper hardware, the deep learning solution based on only 2D images also reduced the error rate of the identification from 2.5% to an error rate of 0.3%. Good. Next step, retrieving of the products. In the process of retrieving the items from the storage, you could imagine to use a robot to identify and pick stored parts from shelves. Basically, the identification is similar to the identification of empty or full shelf positions. The only difference is that the number of possible classes is increased. The previous application had only two classes, like occupied and empty, and this application would need to differentiate a much higher number of items, which could be solved with deep learning. Using 3D sensors, the gripping position could also be determined, and combining these both technologies would then lead to a completely automated retrieving process. The next step in the process chain is the commissioning. Nowadays, saving plastics and packaging material is quite a popular topic. Using 3D algorithms in combination with, for example, sheet of light sensors, one would be able to measure the size and the volume of each of the objects during commissioning, and based on this information, a packaging strategy can be determined in order to save packaging material. As an application example, on the left you can see the sheet of light reconstruction of arbitrary shaped items and the volume of each of these parts, which can be very easily calculated with a few operators in HALCON. For packaging strategies, it might also be very useful to calculate the maximum space needed for some objects. Therefore, algorithms like calculating the bounding boxes can help. Especially in commissioning phase, machine vision can help quite a lot. Another success story is an interactive help for the operators collecting the items. The initial situation was as follows. The complexity of logistic tasks continues to increase, and reciprocally, the performance of employees is decreasing. Temporary workers have to be trained for a long time, and fatigue and absenteeisms are more frequent due to heavy workloads. The solution to this? An image recognition system that functions event control optically and fully automated. The system guides the employee and tells the employee which part should be taken as the next step, and uses a 2D camera to check if the operator used the correct part for commissioning. Here you can see a screenshot of such kind of system. It recognizes the component and the event and reacts accordingly or guides the employee. It displays the next steps on the monitor and checks that it has been implemented correctly. If everything is done correctly, the employee is visually rewarded and the next step is displayed. So the system also recognizes very similar components and products by means of the features like shape, colors, contours, and lettering, which are stored in an integrated database during a teach-in process. Neither rotation nor positioning are a problem for the system, and barcodes can also be read very quickly. This makes it ideal for the use in production, manufacturing, outgoing goods, and incoming goods. You do not need a specialist to teach in new products. Temporary workers and unskilled workers can also do this very easily. And thanks to its skills in identifying, measuring, counting, and checking parts, the system is ideally suited for quality control. So complaints that damage the image of the company and can lead to customer loss and consequential costs can be also completely avoided. Another use case for machine vision in the commissioning process is to identify items and accordingly print the correct information in a bar or data code. A success story from a customer of ours here is an automated vision system that identifies cases of packed fruit and affixes barcode labels at a rate of more than 60 cases per minute. Some product cases are easier to label with barcodes than others. When a single type of product with a uniform size, weight, and variety is packed into cases over a period of many hours, for example, the same barcode can be placed repeatedly on those cases. However, this is not the case with stone fruits such as peaches, plums, and nectarines. Boxes moving down a production line will vary randomly in case type or size, as well as the size and the grade of the product. So the code labeling process must be as dynamic as the packaging line. To enable that products to be tracked through the supply chain, in this case, barcodes are dynamically created and affixed to each of the products. This barcode then contains information about the product, its variety, the relative size, the packaging, the farm where it was produced, the packaging company, and the date of packaging, and many, many more. After printing the code, it is necessary to double-check the printed code quality. Using HALCON, you have the possibility to analyze the printed code quality based on common standards to make sure that the printed codes can be read by any other reading device. Here you can see such a screenshot of such a print quality control of a data code. Each module of the code is inspected and several in standards defined parameters are generated. The critical modules can be color-coded. In this example, we used a data code which is disturbed by different effects to be able to see how bad modules would be detected by the inspection. Last but not least, we've come through the process to the delivery process. The same principle as for the volume determination during commissioning can be applied here on the scale of boxes and pallets. Using machine vision, the volume of boxes which should be palletized can be determined, and this information can be used to automatically and efficiently stack the boxes onto pallets. Based on this 3D information, picking points can also be calculated quite easily. Another idea is to use this information as a final quality inspection to document the quality of each box as it left the storage. As you can see, every process step in intralogistics and warehouse automation can profit from machine vision. In case you have another task in mind for which you are not sure if machine vision can help to tackle this problem, feel free to contact us. We are pleased to consult you or to do any kind of feasibility study. And to contact us, use our website mvtec.com or the mail addresses mentioned here. So far, this is it from my side. I hope you enjoyed this webinar. Before we go on answering your questions, I'd like to encourage you to answer the poll questions we now just activate. Here, we would like to get some input from your side about what you think are the most important topics in the future regarding machine vision. So one question is, which application for machine vision will see the most growth over the next 5 years? Which machine vision technology will be the most important within the next 5 years? And what is the most important to increase adoption of machine vision systems? So feel free, please give us some feedback. We would like to get your opinion on these questions. So we will just look at the results. So track and trace is so far quite common. Track and trace, technology, I see OCR. And the most important looks like is robust algorithms. Now lower costs also coming in. So okay, now the image changes a little bit. More and more people are answering. Very interesting. Okay, deep learning is one topic which is around 50% as a technology coming in the next 5 years. Most important of the robust algorithms for you, and what do we have else? From the application, it looks like packaging and autonomous navigation is topics which are very interesting. Okay, thank you for your feedback at this point, and with this I will hand over to Dennis for our Q&A sessions.
Thank you, Mario. We will now begin our Q&A. Just a reminder, if you would like to ask a question, please use the Ask a Question area to do so. And let's go to our first question. How many images are needed for deep learning?
For deep learning, we recommend to have images in a number of around 200 to 300 per object. This strongly depends on the variance, how different your objects can look like. So imagine if you have natural products, one apple usually doesn't look like the next apple. If you're talking about screws, which basically look totally the same, you maybe will need less images. Yeah.
Next question is, how do you debug deep learning algorithms?
Debug deep learning algorithm is quite difficult. Deep learning, one disadvantage is it's kind of a black box algorithm. So you input images and you get a classifier which returns a result. The debugging basically is data analysis. So when you have a deep learning classifier which does not perform as you'd like, one reason, in most cases from our experience, the reason is in the data you used for training. So we dig into the data, see is there any obvious problem, is there any influence like lightning or other things which is not represented in your training data but occurs in your scenario, in your production floor. So the most important thing from deep learning always is you need to have all the variants which can occur in your online application inside the training data, which might be in some case a problem.
You mentioned lighting. How does lighting impact accuracy?
Lighting does, of course, impact accuracy. We are doing machine vision. We need light. It's difficult to give a rule of thumb here because it strongly depends on what kind of application you use. For example, if you're talking about 3D applications where you use sheet of light technology, lightning is more or less not a big problem. If you have your applications where you measure dimensions and the lightning changes over time, of course this impacts your algorithm. So the recommendation always is to keep lightning as stable as possible. Yeah.
Next question. What is a typical process time for a 3D surface-based matching application?
3D surface-based matching strongly depends on the number of points you have in your points cloud and on the complexity of the surface. There are applications where the processing time is in the area of around milliseconds, 100 milliseconds. But depending on how big your objects are, how big your point cloud is, this can go up to let's say 300, 400, 500 milliseconds. So here it's a matter of what does your object look like and what hardware are you working on, because of course strongly the process time depends on the computational power of your device.
Next question. Can you see using this technology for inventory visibility in retail shops?
With inventory visibility, I guess it's, or let's say, like, if I got it correctly, in retail shops, you would like to use deep learning to detect if the shelves are empty, if you need to reorder some products. For this kind of application, I think deep learning is possible. So you could imagine like having a camera monitoring your shelves, reading the barcode. By this barcode information, then the system knows what kind of item should be placed here, and by deep learning you can see or estimate how much of these products are still available, and in case maybe the shelf is empty, you just reorder automatically your products. So such kind of applications can be applied.
Okay, our next question is, how do you calculate the accuracy of a measurement system that uses machine vision?
It's difficult to calculate the accuracy of a measurement system for machine vision because there are a lot of different factors. So basically it's what kind of object are you looking at? What kind of resolution does your camera have? What kind of lens system do you use in this application? So it's difficult to give a number. A typical process would be to have measured parts where you can compare a real measured coordinates like from another measurement machine and compare this to your measurement results from machine vision. To give like a formula is not possible on this point. Strongly depends on the application, on the lighting condition, on the contrast you have in the image.
Our next question, I think, is related to the question about inventory management on store shelves. Could this technology be used for Amazon Go type item check-in, or even for doing object recognition on items in a cart for frictionless checkout?
So imagine you have such kind of, let's say, several cameras mounted in the area when you leave the shop with your cart. You could use such technologies. The problem is always that somehow you need to at least see the objects partly. So if I'm thinking of a cart in a shop where products are stacked in several layers on top of each other, I think there might be the difficulty to be able to see each of the parts. But basically, yes, if you can make sure that one of each of the cameras can see at least parts of the objects, you could use deep learning technology.
Our next question is, how can deep learning be utilized to sort according to the type and weight of packages of random size and orientation at a fast pace? For example, the barcode or labels are not always readable, but packages have distinguishing features like color and size.
So you could, let me just double check the question to get it correctly. You could use, of course, train some deep learning, the type and weight based on the size. If you want to sort objects, like I want to have all the objects bigger than certain threshold, you could use deep learning for such things, but deep learning is like a classification, so there's no fixed tolerance boundary. Like you could say, okay, I only want to have packages of size exactly 100 times 100. So if you don't rely on this fixed boundary, you could use deep learning networks to train with several images of different kind of boxes in different sizes, for example. Color is also possible. Usually deep learning networks, if you use color cameras, also can use this color information. And the weight, for the weight you would use, weight is difficult because weight cannot be seen. So you could use a 3D technology to determine the volume, but the deep learning algorithms we provide so far are not able to work with 3D point cloud data. They just work with 2D information. So having a quick thought, I cannot think about a way to code the weight inside the image. so far. So wait will be difficult.
Next question. Do you envision a day where today's current barcode technology is displaced by machine vision or computer vision?
That's a good one. I think, or I could imagine there will be a day where our technology is as good as identifying products without any codes and everything. Nowadays, barcode information includes a lot of more information sometimes than just the object ID. Sometimes you want to store other information like when was it packed, especially for the data codes. So I don't think that all these information can be only be tracked by machine vision. And also barcode is so far quite fast in the detection, and there are a lot of standards. So I don't see that in the next time barcodes are displaced, but who knows what happens in 10 years.
We mentioned 3D point clouds. Are there any software solutions available now for 3D point cloud machine learning, or is this still at a research level?
At Emitech, it is still at a research level. So we are working on several ideas to use machine learning, deep learning with 3D point cloud data to use this, for example, especially in case of finding boxes. But so far this is still on research level. As soon as we will bring this to an, let's say, engineering level where we can bring it in a product, we will do this.
This is currently our last question, so if anyone has anything else to ask, we do have a few minutes left. You're going to want to ask that now. Next question is, do I need to know the exact code type of a bar or data code before decoding?
No, you don't. Using HALCON, you just need to know if it's a data or a barcode, because there are different algorithms to detect these two kind of codes. But even then, if you could use both on one image, the decoding speed is quite fast. The only advantage, in case you know the code type, like for example it is a QR code, is that the processing speed will be faster.
Okay, we actually will make this our last question. How would you differentiate computer vision from machine vision? Is computer vision basically the evolution of machine vision, i.e. machine learning and deep learning?
So I don't think that like deep learning is the evaluation of, like, if the question goes in this direction, like is deep learning in this particular case the evaluation of the traditional machine vision? We don't think so. We don't think you will need to use both to get the most of your applications, because there are still a lot of applications and a lot of tasks in machine vision which cannot be solved with deep learning so far, and we think in the future will also not be able to solve. So for us, deep learning and this new machine learning technologies is just a new method in the big box of machine vision technologies, which you can use as a tool base or a tool case to select the tools you need to solve any problem in machine vision.
I do want to ask this new question because it's interesting. Where is deep learning technology in terms of this? They're asking package within smartphones or handhelds, but generally speaking, can you run deep learning software on a smartphone?
Basically, yes. Our software we have ports on demand available for Android and iOS, and so you can use our machine vision library on such kind of, let's say, operating systems. On all of these phones which are based on ARM processors, as I mentioned, you can do deep learning inference, means the classification task. On an ARM processor, you are could also use a smartphone with this kind of technology.
And what are the most significant advantages of using specialized cameras like line scan cameras in comparison to a regular smartphone camera?
The difference between regular smartphone cameras and the cameras we usually use, like industrial cameras, is that they are made for a completely different market. Industrial cameras are made for production scenarios. They have a very low noise to signal ratio, because they need to focus to get real good picture quality for machine vision tasks. A smartphone camera basically is there to make pictures which look good for human eye, and that's a difference in the quality of the image. By human eye you will not see, but if you're working with algorithms, they will be different. As there was mentioned, the line scan cameras are especially then interesting if you are using a moving scenario, like you don't want to stop. For example, you want to get an image of a part which is not stopping because your conveyor is continuously running. In this case, line scan cameras can be used because they just collect all the information from one line which is passing under the camera and then return it into one image as soon as the part passed the camera. So this would be one advantage of the line scan to a usual camera. And the difference, industrial camera, smartphone camera, is just that they are produced for a different market.
Okay, with that, on behalf of Vision Systems Design, I would like to thank Mario Bohnacker and all of you for joining us today. This presentation will be archived within 24 hours and can be accessed from the homepage at visionsystems.com. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. If you have any questions about today's presentation, please feel free to email me at dsemeka@endeavorb2b.com. We thank you again for joining us today and look forward to providing you with webcasts in the future.